point is we're using limits now to build things like rates of change. So that's where we are. And in this particular section, we're talking about two different types of rates of change. And that's one of the major topics of calculus is derivatives, which is a rate of change. And so let's dig into it. Okay, so oftentimes, and this is important because of what it says at the top here. I'm just going to kind of paraphrase what it says right there. But generally, when we're modeling things, and I do mathematical modeling in my own work, we often want to like think about what's going to happen in the future, right? Like we think about how many cases of coronavirus are there going to be next week, right? Or we care about polar bears or something. We want to know how many polar bears are going to be in 10 years or whatever it is, right? We want to know something that we usually project into the future. Well, what that usually involves then is thinking about how the system is changing and then projecting that change forward. And in calculus, we think about changes as derivatives. And so that's what we're at right here. And we're going to talk about two different types of rates of change, right? And so the first type here are all type A. I'm going to highlight those all in green because those are all similar to each other. In the first instance, you could think about two different ways a moose's weight changes, for example. Let's say we're a moose researcher. You might care about how much weight is gained over the first 10 years of its life. That's a different kind of rate of change than type B, right? Which is how's the weight of the moose changing exactly when it's 200 hours old, right? One sort of over a long period, one's at a very specific moment. The second thing is talking about how is the concentration of a drug in a person's stream changing. We might care about that changing. How does it change over the first couple hours after ingesting it? Or maybe we care at a very specific moment, like 25 minutes after taking the drug, right? Or the third example maybe I'll share is um, this is out of a textbook that was talking about federal spending on stem cell research. If we care about long term kind of general changes, we might care, well, how has it changed over the last 10 years? If we're hyper focused on what's happening right now, we might care about what's happening in 2007 or 2021 or the specific year we care about. Now, each one of these things, each one of these examples, these specific examples, is kind of contrasting something over a period compared to something at a specific moment, right? And so that's getting at these two different types of rates of change. Type 1 above, or type A, I should say, those are all what we call average rates of change. And you can see, like it says in the description, this is sort of talking about what happens on average, right? It happens over a period rather than what happens at a specific moment. So let's dig into the moose example. And I get some of these examples from this textbook I used to teach out of that talks a lot about biological examples. And so they had a function in there that was talking about how much weight a moose, or how much a moose weighs, I should say. And one of the things they were saying is a male moose might gain 500 pounds in the first 5 years of life. Oh, sorry, in the first 5 years of life. How much weight do they gain on average per year? Right, that's the question of the average rate of change. I feel like anyone can answer that, and I would love to hear someone chime in. How much weight do they gain per year?
100 pounds.
100.
100. Yeah, thank you. A couple people answering. That's wonderful, right? 5 years, 500 pounds. Really easy just to set up. Well, they gained 500 pounds in 5 years. That's very easily 100 pounds per year. Right, so that's just an example of an average rate of change. Now, again, it's over like 5 years, and so we're not saying every year they gain exactly 100 pounds. They probably didn't gain exactly 100 pounds any year, right? And there may be places where they gained a lot of weight. They may have lost some weight over that time. They probably did, right? Most mammals lose weight over the winter, for example. Well, not us mammals, but most mammals that live in the wild lose weight over the winter, right? So they might go up, go down a little bit, go up, go down throughout the 5 years, and we're just saying like on average over that span they gained 100 pounds per year, right? So you're gaining general information, nothing very specific. Let's contrast that with type B, right? Type B, and maybe I should use a different color. I'm going to go back up here and use blue just so we can write in blue. It's not easy to, oh, maybe purple's fine. Can't really write in purple or yellow ink. So anyway, all those type B things up the top there, that's what we would call instantaneous rate of change. And in calculus, we refer to those as derivatives. So that's, we're building towards this word called derivative. Or we're actually going to introduce it right now. But the point is, these things are happening at an instance. Okay, it's happening not what is the moose gain over 5 years, what's happening right now, right? And so maybe an example of that in terms of this moose thing would be, you know, at 65 days old, that's still a baby moose, right? Yeah, a baby moose is gaining, let's say, oops, that's not gaining. I'm just totally making this up, 5 pounds per day. So again, that's like hyper specific on the 65th day, how much pounds are they going to gain? Now this is really, really specific. And so you wouldn't want to use this information on day 70, for example. This is just applicable to day 65. Now it tells you what might happen in day 70, right? Like in day 70, we might expect this thing to be 20 pounds bigger or so, but we're not getting exact results there, right? We get some very specific things on a day, not sort of anything around that day. Someone say something in the chat here. Oops. Oh, I see this question that Simon asked a little while ago. I'm sorry, Simon. Maybe we can get to that towards the end here. Question about the difference between those two things. See what I'm saying there about how one's over a period, one's hyper-specific, right? One sort of gives you general information over a time span. One's very, very specific. The thing that we're eventually getting into here is the instantaneous rate of change. As I mentioned, that's a derivative. That's one of the main focuses of calculus is this concept of a derivative. And I'm going to highlight the part that's relevant to us in calculus. We represent that with this notation F apostrophe with a point at A, right? So this thing that I'm highlighting, F prime of A, which is one way to say that, or the derivative of the function at A, that's telling us how the function is changing right at that very point A. Okay, and I'm going to draw some pictures to kind of illustrate this concept over the next couple periods. Questions so far? Questions at all? Okay. So you can look on the next couple pages. Let me just monitor the chat. I should have the chat up here just in case something happens with that. Over the next couple pages, we're going to dig into these two things, right? So, sorry, just getting distracted by my email. So on the first page, we're going to dig into average rates of change, right? So this is going to be the, did we use green on that one? Yeah, this is going to be the green stuff. And then on the second page, we'll dig into the instantaneous rate of change one, which is the purple stuff. So one thing at a time. I think my guess is we'll probably definitely get through this page. I don't expect to go too much farther than this. I'd like to ask you to try one at the end of class. And then I want to talk about taking attendance. I've had a hard time taking attendance in class, so I'm going to ask you with your help for that. Anyway, just kind of previewing what's happened here. So average rate of change, like I said, it's over a period. And so if we want to calculate average rate of change, it's very straightforwardly given by this formula, right? The average rate of change given by the function f of x over some interval x1, x2 is given by this, right? So it's either we're thinking about how the function changes divided by how the x values change, excuse me. And so there's three ways to look at that, right? This is sort of an intermediate notation. And the actual thing that we really care about is the last expression, right? We're plugging in the function values on the top. We're subtracting the function values on the, or the x values on the bottom. I also just want to add, if you're not familiar with this, oops, with this notation, the triangle here. Does anyone know what that is? The triangle. So it's not a triangle; it's a Greek letter. I don't know what that one is.
Delta.
Changing.
Yeah, it's delta. So it means changing, exactly. I didn't mean to put parentheses around that. Quotations made. So the delta means change in. It's something you see in not just future math classes, but lots of science classes as well. It's a good thing to know. So the change in part is where you subtract the two values, right? If you want to know the change from x1 to x2, you subtract x1 minus x2. So what else does that look like, right? This should kind of look familiar, like something that you see in previous classes. I know I harp on pre-calc a lot. We see this in pre-calc, but we see it in lots of other places too. What is that?
The slope formula, right?
Yeah, that's a slope formula, right? That's the definition of the slope. But the slope of what specifically? The slope connecting two function values. So it's the definition of the slope of the line that connects f of x1 and f of x2. So we're going to draw a picture of this right now on the graph spot. But that's sort of what we're thinking about. All right, and that's why we get this average rate of change, because we're just like doing a slope between 2 points, and we're going to miss the intermediate parts. All right, so let's start drawing this. So let me set up my picture down here. So we care about two x values, x1 and x2. Let me draw the graph first, actually. Try to draw a graph that looks like this. So that goes up, down, and then kind of goes back up again. That's going to be our f of x. And then we care about two x values. And so let's label x1 and x2. I'm going to make x1 kind of on that hump right there. All right, so this right here is f of x1. And let's take x2 kind of farther down the line so that it lines up above that point. Right, so first of all, notice the x values are on the x-axis, of course, but the f of x values, those are y values, right? So f of x1, f of x2 are outputs. They're function outputs. They're on the y-axis. And so this thing that we're trying to do here, this formula that I'm circling, is just the slope connecting those two green dots on the line that I drew. All right, let me make those dots a little bit bigger so we don't lose them. Right, so this thing I'm trying to show right here, this line is literally what we're doing, right? We're just calculating the slope of that line. And kind of the key takeaway, the thing I'm trying to harp on, that I hope it's not too annoying, but I'm going to write it down one more time, is that we're not getting specific information about this, right? We're getting very general information. In fact, based on the picture I drew, the average rate of change would be positive, right? Because the slope is going up. But this graph went down in between them, right? This graph actually goes up, and then it goes down, and then it goes up again. But the average rate of change would only capture an increase because we're doing a general thing. So we don't get that in-between information. We just get a general understanding of what happened, right? So note, we're not getting specific info. And, you know, I sometimes go back and forth about whether to write detailed stuff about this, because I know sometimes people don't write this stuff down, which is your choice. The reason I do is because when you go back and look at this later, it needs to make sense later, not just tomorrow, but a week from now when you're working on the homework, or 2 weeks when you're studying for the exam, etc. And if you just write this kind of stuff down, you'll be able to read this later. So we just get the general trend of overall change. Okay. All right, think about the moose weight example. This could be a function of the moose's weight. It goes up, it goes down, but overall it went up, and so we get that average rate of change. Questions about that at all? Okay. Let's do a couple examples. How are we doing on time? We're doing great. So let's do that moose example. So here's an example that's actually implementing what we just did a second ago, but with a function. So the weight of a female moose, it says right here, is given by this function, right? Where t is measured in years. Right, so we have a real function to work with. You plug in a t, it tells you the weight of this moose in kilograms. What's the average rate of change from 1 to 3? Right? How does it change overall? Again, it probably goes up and down in between there, but overall, what happens? Well, really easy just to implement this formula that we just used, right? So we'll do the average rate of change. I'll abbreviate rate of change occasionally, ROC, from t equals 1 to t equals 3. That's what we care about. Well, that's going to be the change in weight. I'm just trying to write the details out just one time. Change in weight from 1 to 3 over the change in time. Who's having a hard time seeing the bottom of the screen? Can you see everything I wrote right there? I think it was Josh. Does that seem okay? Okay, so the change in weight, we just plug those function values in, right? So we're going to do this kind of thing up here. We're just plugging the function values in. And so we're going to do W of 3 minus W of 1 over 3 minus 1, right? So on the top, we're plugging things into the function. On the bottom, we're just subtracting the inputs. And note, we want to have a unit here. So it's helpful to note that on the top, we have kilograms, and on the bottom, we have years. Because that just shows us that the unit's going to end up being kilograms per year. And so we just do these things, right? You plug those numbers in. When you plug in 3, you get 440.8. So moose will gain 440 pounds in 3 years. That's a lot. Female moose, at least. And then 2 years on the bottom. Real easy, right? And then you just do the subtraction, divide by 2. So on average, 48.8 kilograms per year. And this is a female moose, so maybe the male moose is closer to what I guessed. I don't know. Right, did they lose weight throughout there? Probably. Were there years where they gained more than 48? Probably. Did they ever gain exactly 48.8? Probably not. But just overall average trend, that's what we looked at. It's okay.
Where'd you get those numbers in the numerator?
I plugged them into the function. So when we write down W of 3, W of 1, here's W of t. So you plug the numbers into W of t to get those. And I just did it ahead of time, right? So it's like 369 times 0.93 raised to the third times 3 to the 0.36.
Sounds
I
good.
should just plug in t values. Other thoughts?
Isn't this kind of like y2 minus y1 over x2 over x1?
That's exactly right. Yeah, so that's what we were saying up here. This is literally just the definition of the slope of a line, which is exactly what you just said. Yep, that's exactly it. Which is what I was trying to say in this picture, right? We're just calculating the slope of that red line. It's just connecting the 2 points. Yep. Keep the questions coming. That's great. Thank you for thinking about this. More stuff. All right, let me do one more example, and then I'm going to ask you to try the one at the bottom here. Oftentimes, people see this kind of thing when they're talking about average velocity. Like that's something that comes up a lot in physics. I don't know if you're taking this class because you want to take physics later, but if you do, you look at velocity a lot of times in physics, and just know that velocity is a type of rate of change. And I think you know that, right? Like if I said, when you get in a car and you drive and I said, what's your velocity right now? You'd say, oh, well, it's 30 miles per hour, right? So miles per hour is your rate of change. And so I'm just trying to introduce right here this concept that we're just using the exact same thing again, right? It's just change in position over change in time. So change in the y values divided by change in the x values. But it just has specific applications that oftentimes come up. So for example, another really easy one, right? If we drove from Fitchburg to Philadelphia, which is approximately 300 miles, and it took us 5 hours, I think everyone could tell us approximately what our speed was, right? What was your, you told your mom that, and she said, what's your at? Whoa, wow, you were going on average blank. Everyone would just say, oh, well, you divide 300 by 5, and you get the average velocity. But just trying to bring it back to the context here, we're actually using this formula, right? So average velocity is change in position over change in time. That's supposed to be a triangle. The change in position, you went 300 miles, right? So 300 minus 0, you start at 0, you went to 300. That's miles. How long did it take? You went from 0 hours to 5 hours, right? And so it just ends up being 300 over 5. And again, I know everyone probably knew how to do that. I'm just trying to point out that you're actually using this formula when you do that. And we would say, oh, well, we drove 60 miles per hour. And I don't think anyone would claim that the entire time you were driving that fast, right? You start at 0, take some time to get to the highway, maybe you stop for coffee, whatever. But overall, you on average went 60 miles per hour, right? I hope that kind of illustrates the average rate of change concept there. All right, I'm gonna ask you to try the next one on your own. So are there questions about the formula or how it works, anything like that? I gotta get some different options in this room. Wanted to do like some breakout rooms. I don't see that option. I gotta fix some stuff. Maybe if I stop sharing, I can do breakout rooms. Let me see what happens. Nope, no such thing here. I gotta fix my options. Okay, let me share again. So I'm just gonna ask you to set this one up then and just think about it on your own. Shouldn't be that tough. This is another one that's got a cool application, I think. How do you get rid of that now? Like, where the heck did the search box come from?
If you click the little magnifying glass at the top of it.
Thank you. Yeah. Well, I actually remember that because I spent a long time one time on some app trying to figure that out and ended up having to look it up. That was one of those embarrassing times for me. Okay, so this is an application. Everyone, I don't know if anyone's ever seen this function or this equation before. This is a very common kind of thing you might see it again in a physics class. This describes a change in motion, in this case, height of an object. So you oftentimes see this in physics where it's like, oh, someone threw a ball off a roof and it's like going towards the ground or something like that. Anyway, so this particular function we're saying is telling us the height of a kingfisher, which is a type of bird, from the water t seconds after it dives. And so it's given by, the setup is given by this picture right here. Let me just hone in on this picture. Right, so this picture right here is sort of the situation. It's like we have water down here. Kingfisher is a type of bird that will start up top here, maybe in a branch, and then it'll like dive down into the water to fish. And so it might be on that trajectory and it's modeled by this equation. This is legitimate, like was what I'm trying to say. This isn't just some made up thing. This is real. And so we might want to know how fast was that thing going over that time period. Wow, it like bolted into the water. How fast was that thing going? Well, we could calculate that. And so I'm going to ask you to use it, to try it using this function. And so if you know what you're doing, this makes sense, give it a go. If you want me to just keep talking for a second and set it up, then let's do that, right? So this tells you the height, right? H tells you the height at a given time. And so we want to use that. I don't know what I was going to say there. So we want to do average velocity. We want to do the change in position over the change in time. My goodness, I think I just clicked something on the right-hand side of the screen. Jeez, okay. Change in position over change in time. And H tells you the position, right? So you want to plug things in to the position formula, and we're doing it over the first 2 seconds. I should have mentioned that too, right? So that's from 0 to 2. So take a second and try that one. This should feel comfortable to you. This is the kind of stuff that's in the homework for next week, and is the kind of thing that's going to be on our first test. So let me just sort of continue slowly doing this one. All right, we want to do this. And it's somewhat easy to plug these numbers into this function, right? 2 squared is not too bad. There's no decimals or anything. And so it ends up not being terrible. I'm just going to give everyone a minute to think about this one. And the thing I would like to also ask you is, there's going to be something weird about the sign. So it should be a negative number. You'll end up with a negative number. And why is it negative is the question I would pose. All right, I'm going to stop here and see if anyone has any questions. This is a real situation. I'd be walking around and see if there are questions. Tommy, you say something?
No, that was me.
Oh, John, what's up?
The numerator H2 minus H0, shouldn't the 2 be 20?
Shouldn't the 2 be 20? Is that what you said?
Yeah.
So we're trying to evaluate the velocity over the first 2 seconds. And so we want to, so 2 is the end second and 0 would be the starting second.
Yeah, but is the top's the position, so shouldn't the first number be 20 since it starts at 20?
So it's the change in position, right? So it went from, oh, I see what you're saying.
Yeah.
Wait, no, now I'm confused again.
It starts at 20 and then it dives down to 0.
Right, so that's the H of 0 time. Right?
I don't know. I'm just going to follow along.
So it starts at 20. That's correct. But we're trying to think about the overall change. And so, yes, it changed by 20 over that time period because it went from 20 down to 0. But that's not really how we're thinking about it. We're not trying to like look at the graph and calculate it. The graph is nice because it kind of paints the picture. We should just be taking these numbers and plugging it into the function. We want to see where were we. We want to see where were we at 2 seconds, where were we at 0 seconds. Sorry, what was that?
I don't know if I'm right, but actually, no, let me just wait for everybody else.
Okay. Other thoughts before we keep going? I'm gonna plug those numbers in and see what happens. So when you plug a 2 in, you'll get
If you plug in 2, you'll get 0, right?
Yeah, exactly. You'll get 0. You'll end up with 20 plus 20 minus 20 plus 20. So you get 0.
And if you plug in 0, you'll get 20.
Correct. So just like John said, we started at 20.
So it'll be 10, right?
Oh, I see. You're going for the answer. Sorry. Yeah. And then we divide by 2 minus 0, and so that's 2, and so that's seconds. And so we end up with minus 10
Oh,
feet
minus
per
10.
second. And this is the thing I was trying to get at originally, and I was sort of trying to clarify with John a little bit, is if we just think about, oh, well, it's 20 on the top, we lose the negative sign, and that's actually something that means something here. So let me just pause and talk about the process and then the number -10. Is it okay reaching that before we interpret it? John, does that clarify what you were thinking about before at all?
Yeah.
or-
Yeah, I understand now how like it goes from like in a real like life sense how it goes from like 0 to 20 and how it's negative. Yeah. I get
Yeah,
it.
because it's going, and so maybe I don't know if you know the answer to this, but and Gregor got that too as well. Nice. What does the negative sign mean? What's that telling us about this situation?
It's going down.
It's going down, yeah. So it's negative because the bird is going down or traveling down, whatever you want to say. So with velocity, there's usually a direction involved, and negative just means it's going from somewhere high to somewhere low. If it was like going from the water back up into the tree or something, it would be a positive value. So I'm just going to maybe add that little note at the bottom. Velocity. In velocity, so in velocity, the sign tells us direction. Usually positive means like forward or up, and usually negative means backwards or down. Like in the going to Philadelphia example, 60 was positive because we're sort of thinking about we're in Fitchburg and we're sort of moving towards Philadelphia. But if we went the other way, maybe it would be a -60 because it would be going backwards towards Fitchburg, something like that. What do you think?
I have a question.
Yeah.
Philadelphia example.
Yep.
So you're going from Fitchburg to Philadelphia, you're starting from 0 to 300 miles, right?
Well, what I'm trying to say is that choice is relative, I would say.
Because what I'm confused is because you put like on the first example you say 300 minus 0, and on the second one 0 minus 20, but they're both starting from 0 and they're both going to a certain,
So in the second example, they're starting at 20 actually, right? The bird's like in a tree or something and it's diving into the water.
Oh, okay.
They're on different planes. One's on the X, one's on the Y. So it's what makes
Yeah, and I wouldn't get too caught up in like, oh, should it be positive or negative? Just know that one means one direction and one means the other direction. And in the Philadelphia example, which direction is forward and which direction is backwards is just relative, right? And all I'm trying to say is if we're talking about going one way, we'd make sure it's positive, and we're talking about going the other way, we'd make sure it's negative. It makes more sense in the bird example because it's like, oh, well, it was high and then it went down, and that's a little more easy to interpret, I would say.
Yeah. Thank you.
Yeah, good thoughts about that. Other questions like that? But I'll just reiterate it again because it's kind of back to John's original question. Instead of trying to think about this in terms of like, where did they start, where did they end, just follow the formula, and then you don't have to think about those things. You just do the end point, h of 2. Let me highlight what I'm talking about, this kind of thing. Like just plug in the last point, plug in the first point, and then the math and the signs will take care of itself. Right, so just make sure if you're just following this function, you don't really have to think about, for that formula, I mean, you don't have to think about positive or negatives. Okay. I'm going to set up the next thing. We won't really get into instantaneous rates of change today, but I would like to talk about the concept. And I just need to open up this web applet that I forgot to open up before. Just give me 1 second.
Professor, I can't
Hey,
hear you.
I can't hear you.
Thank you. Thank you. I accidentally clicked off my mic. So what I was trying to say is, in an instantaneous rate of change, we're thinking about at a specific instance, right? Think about the difference between these two things. Average was over a period, instantaneous at an instance. And so average, like we just looked at, is like the slope of a line. Well, with instantaneous rate of change, we want to be looking at a very specific point and what the rate of change is there. And so what that looks like, let me share my computer screen and show you this. Let me move it over here. Share this. The idea is, and let me go ahead and make this function look more like the picture we just drew a second ago. So let's flip it upside down. And that's fine. So the instantaneous rate of change would be, this is currently showing the average rate of change between A and B on this picture. Right, let me just make sure I'm showing what I think I'm showing. Yeah, so it's currently showing the average rate of change between these two things. And I can draw on this. This is average rate of change from A to B. Literally the picture we were just looking at before, right? You're connecting two dots. And you can slide this around a little bit and move the points, is what this applet lets you do. You can kind of move the points around. You can make them closer to each other or not. Now, the instantaneous rate of change, another way to say that is it's the slope of the tangent line. Now, even though this curve, the black curve, looks curved, right? The graph function is obviously curved. If we zoom in close enough at a location, it'll look like a straight line. Right, so I'm just going to start zooming in on this graph. It still looks curved, right? But if I get close enough, it's going to start to look like a straight line. And so the idea is, if you hone in really, really close at a spot, right? So right one instance, it becomes straight. It's already looking very straight, and I'm not really even that close, right? The closer you get, sort of the straighter this thing is going to look. Let me just go ahead and refresh and get back to the original. And so that's what we're trying to do here. We're trying to measure the steepness of the line at a very specific spot. And it's given by a limit, because notice how as B, I'm going to shift this slider, and as B gets closer and closer to A, the blue line that connects them gets closer and closer to being the tangent line. In other words, if I zoom in on that spot again, if we move them kind of far away from each other, you get an average rate of change thing, right? But as this point B gets closer and closer to A, it essentially approximates the straightness of that line at that location, right? So I'm zooming in again, and you can see it's still doing an average rate of change between those things, but the blue and the black line are like right on top of each other, because it's kind of approximating how curvy it is, right? And again, the idea is, like, if B gets closer and closer and closer, it eventually will approximate the exact steepness at that location. I'm going to switch back to my iPad in a second and show you the notes, what this, the implications of this in the notes. But are there questions about what I'm trying to say from this applet before I switch back? So I'm just going to look at this in terms of the limit. So that's exactly what it says right here in terms of the exact value of this derivative, right? It's the limit as the 2 points get close to each other of the average value equation, right? This thing is just the average rate of change that we just looked at. That's the exact same formula, right? But the added thing is that we now have a limit associated with it, right? This is the new thing. And so when x approaches b, that's like the 2 points getting closer to each other. And then when it equals b, you end up with the slope of the tangent line, which tells us the steepness of the graph. Questions about what I'm trying to say there? I'm going to draw that picture on this one. I'm going to draw the picture that we just did a second ago right here. So we have this like upside down minus x squared kind of curve, right? And I'm going to try to recreate that picture I just did a second ago. And let me add a couple words before I do that. So this formula right here, this is a super important formula. I think I might throw a red box around it. Actually, it's that important. This is the exact value of the instantaneous rate of change for the function f of x at the point x equals b. And what I've explained it before is that we denote it with f with the apostrophe, right? So we call that the derivative at the point b. And I'm going to try to draw that picture we just drew a second ago as well. So wondering if there are questions. So far, so good. So in that applet we just saw a second ago, by the way, this is method 2, right? I'll talk about method 1 in just a second. Method 1 is just the estimate. I thought it would be helpful maybe to look at method 2 first. So in that applet, we cared about some point. I'm going to call that point B. And we wanted to know the tangent line at that point. And in order to get that, we do a limit as x approaches B. And so x approaching B might be down on the x-axis like this. Like here's x1, maybe this is x2, x3, right? These things are getting closer and closer to B. So what I'm trying to show down at the bottom here is this is the limit. This is going to be x approaching B right here. And the idea is we want the slope at that point that I'm circling right now, right? We want the slope of that tangent line. And in order to get that, we do a bunch of average rates of change and allow them to get closer and closer to B. So like the first one.
Could you scroll down just a little bit?
Is that good?
Yeah, that's good.
Right, so if x is far away from B, do this with these dotted lines here. It might be like connecting those two. And then as x gets closer and closer, the lines are just going to get closer and closer. Right, so this one might be like x2. Maybe x3 is right here. And ultimately, right, as x actually reaches B, we end up with that tangent line. So I'm doing that one in blue here. I make that one 100%. That's the one we really care about. We want the slope of the blue line. And so what I'm trying here is f prime of B tells the slope of the blue line. And we obtain it using this concept of a limit. It doesn't look great. Let me try to adjust that a little bit here. It's a little better. So I'm just trying to like draw what I just showed you in the applet, and I know it's kind of hard to do, but that's my best go at it. Can I answer a question about what I'm trying to say here? This is why we talked about these limit techniques, right? Because this thing's going to end up being indeterminate most of the time. We're going to try to calculate derivatives. That's going to end up being indeterminate, and we're going to have like techniques that we know how to solve it. I'm going to write down a few more things, do a few more clarifying thoughts here, but are there questions? Let people catch up writing questions about what I've said. So when people look at this function or this expression, they oftentimes get really confused when it's time to actually do stuff, right? So x is a variable, b is a number. And so f of b is also a number, right? And so it's important to realize those things when you're actually thinking about this. So I just like writing this stuff down because people get really confused. So f of x is just the function that we care about, right? And x is the variable. It's just x. F of b is f of x with x equals b plugged in. So it's a number. So we have like a function minus a number on the top. And then on the bottom, you have something similar too. B is also a number. V is a specific x value. And so again, I just think writing this stuff down will be helpful. Once we do an example, next class probably, you'll be able to look back at this and say, oh yeah, I see what you're saying now. And that's the kind of key point that is said sort of throughout, but really can't emphasize it enough, is that when you take the derivative of a function and you plug a point in, it'll tell us the slope of the tangent line. At f of b. And the way to think about that is it's thinking about how steep is the function there. It's a measurement of how steep is f of x at f of b. Slide up for those folks who need that.
Because it's interesting, but not as useful, obviously, as the exact value. Okay, so what this is saying is we can approximate the limit, right? So there's an approximate equal sign right there. We can approximate the limit shown below by doing an average rate of change between two places and then averaging those two rates. So let's draw the picture again. I know that was confusing sounding. So let's draw that same picture. I'm just going to redraw this picture right up here. Not the exact picture, but the function at least. And again, we're interested in some point B. So let's just put that point right there. And we want to know the instantaneous rate of change there, which I will again just represent with that dotted line. Right, that's what we want. Oops. We want the slope of that line. Sorry, we don't want that line. We want the slope of that line because if you remember, it's like if we zoom really, really close to the function, it's like that's what's going on right at that function. It's telling us how it's increasing or decreasing. Okay, so we want the blue line, the slope of the blue line. And so what this method is saying is we can think of a couple points near B, right? We care about the point B, but we can look at a couple places near B that will actually allow us to estimate this. I'm actually just realizing too, what people are talking about looking at my screen here about the bottom getting cut off. The bottom gets cut off because of the bottom of, how do you make this go away? Like on my screen that shows more stuff. Anyway, sorry, I just got distracted there. This is page 18, yeah. Sorry about that, I got a little distracted. So what this formula is talking about is we can look at a place a little bit before A or B and a little bit after B. So let's label those places. Let's label A and C right there. Right, you can see it says B is between A and C right at the top there, right? And so what we're going to do is we're going to do the average rate of change from A to B, the average rate of change from B to C, and then we average those average rates, and that will approximate the middle one. So the idea is this, in other words. I'm going to get my line number, my lines out here. So here is f of A and here's f of c, right? We're going to do a dotted line between each one of those points and the point we care about. So like this, in other words. I guess I should maybe use different colors here so that we can color code it a little bit. Come on. My goodness, I'm sorry, this is getting so jerky. I don't know why it's being so sensitive here. So what I'm trying to say is the green line is given by this piece, and the purple line is given by this piece, right? So we've got the second one right here, and the first one right here. See what I'm saying there? We're just doing the average rate of change a little bit before B, the average rate of change a little bit after B. So one of them's too big, one of them's too small, right? Like one's too steep, one's too flat. And then when we average the two of them, it gets like approximately right is the idea. Right, so we do, let me just maybe make a quick note of that on the side here. So what we're doing here in this method is it takes the average rate of change from f of A to f of B, so a little bit before B, and from f of B to f of C, and averages those rates. So again, it's just an approximation, right? So this is an idea of if we didn't know anything about limits and we didn't know the techniques we've been learning about, we could just approximate these things just by using average rate. So people get what I'm kind of seeing there. I know it's a little bit of a jumbled thing. I'm trying my best. Thoughts? Questions? What do you think about that? Anyone online have anything to add there? So how do we get a good approximation? Right. In other words, how do we choose A and C? We know point B. B is the point we care about. But how do we choose points around B to get a good approximation? Thoughts about that? There's a couple of things that would like ensure we get a good approximation. What do you think? Yeah, we want to get like close to B. We don't want them to be way, way far away because then the function might do other dippy things, right? So no, closer to B, the better. So the closer A and C are to B, the better the approximation. I'll just note too that you want to do like an equal interval on either side too. Maybe that's obvious, but you don't want to do like 2 away from it on one side and only 1 away from it on the other side because that's going to be a little wonky. You want to be like an equal interval around B. But otherwise, it's pretty arbitrary. And in the homework, it tries to get you to pick specific numbers. It gives you like tables and stuff to pick numbers out of. But if on a test or in practice in general, you just have to choose numbers close to B. That's sort of the idea. And I think maybe I should just clarify this even further because I haven't written it down. I have a note here about it. The blue line is what we care about, right? We care about the slope of the blue line, and that's what we're calculating here with the derivative. This is the slope of the blue line, and that's what we're trying to calculate. That's the whole goal here. We're trying to calculate. All right, that's it all. So we've got an approximation and we have an idea about how to do the exact value. And the next couple of pages are just a bunch of examples of doing those things. So are there questions about the concept at all before we look at that? So some of the ones I just mentioned, the ones in the homework sometimes have a table, for example. So they look some of them look like this, where in this particular example, we're thinking about C being some concentration of drug in the bloodstream. Right, so I always do the example, oh, you have a headache, you take Advil, it takes a while to go into your bloodstream, right? And it's being measured in parts per million, and T is given in minutes, right? So you plug in a T, it tells you how much parts per million is in your blood. And this question wants us to estimate specifically the instantaneous rate of change at 0.2, right? So this is the one we care about. We care about this moment, but we're going to estimate it by looking a little bit before that point and a little bit after that point, right? So we're going to do this idea that we just talked about. We're going to pick a B or an A and a C and estimate it, right? So let's look at like color coded again. We'll look at the average rate of change from here to here, and then we'll look at it from here to here, and I'll use those two colors, and then we'll take the average of those two things, okay? So let's see. So the derivative C prime at 0.2 is approximately, right? This is the squiggly equal sign is important. It's showing that we're not being exact, we're approximating this. And I'm going to use the formula above there. So it's 1/2. Let me start using my color codes here. Oh, I'm not going to easily be able to get into that color code. How do I get another color? Maybe this one. Right, so that's the blue part. That's the blue. This is supposed to correspond to this thing, right? And then we would add to it the other one, which is given in green. So if you just look at the formula right at the top there, it's exactly what we're doing, right? We're looking at the average rate of change a little bit before the point we care about, which is 0.2, a little bit after the point we care about, and then the 1/2 is averaging them, right? This 1/2 right here that I'm circling, that's averaging those two things, right? When you add two things together and then divide by 2, it's averaging it. Thoughts about that setup? Maybe I'll just make another quick note in case this isn't clear, in case someone's lost but doesn't want to say anything, right? This is the average rate of change from 0.1 to 0.2. And this from 0.2 to 0.3. Anything? Seems okay? And if we had a function, we'd plug the numbers in and get those values, but it's just a table, and so we can just pick those values right out. So we don't even have to like calculate anything, we just have to pull them right out of the table. Let me switch over to black ink here and finish it off here. So this is 1/2 0.94 minus 0.89 for 0.1. I'm just pulling these numbers right out of the table. Something's not right here. No, that's right. Yep. And just calculate it, right? Really easy to do. We get 0.45. What are the units? I forgot to write my units in there. Thoughts about that? We've got parts per million on the top. On the bottom, we have time. I guess technically minutes. Yep, go ahead. Nice. ppm per min. That's our takeaway. What does that mean? That's the whole point here, right? We want to like learn something about what this is saying. Yeah, as a minute goes by at this rate, 0.45 ppm would enter your bloodstream. But notice that, just kind of looking back up at the curve here, it would be like we just calculated the slope of this blue line, right? But that slope only exists at that very, very point. And as soon as you step right to the right of that, like here, for example, it's going to have a different slope. And so that 0.4 ppm is highly localized. And so, when John says after 1 minute, 0.45 will enter your bloodstream, that's if it was going to stay at that rate, right? And so, in other words, we wouldn't want to assume that a minute later it would go up by 0.45, but that's like a good estimate about what might happen. Right? Does that make sense? It's like we're going up this way. It's like you're walking up a hill with your eyes closed, right? You know how steep you are right now, but when you take that next step, you don't know if it's going to be the exact same steepness again, right? It might go down, it might go up. You don't exactly know, but it's a good estimate. You're kind of at this steepness, right? And you take a step, it's probably going to be about the same steepness later if you take a small one. Anyway, one way to think about it. So I was just going to write that down because we do want to interpret this stuff. So this is, oops. This is telling us, and there's a positive number too, which means it's going up, right? Of course. So we're still ingesting it. So at 0.2 minutes, the concentration is increasing by 0.45 ppm per minute. And I just can't say it enough times because that unit is a little bit misleading. ppm per minute. It makes you think like, well, next minute is definitely going to go up 0.45. Just saying at this current rate, that's what would happen. All right. Is that okay? The estimate part, the estimate. Yeah, let me just let people finish catching up here. See if there's anything in the chat. Like it. Concentration. Yeah, I don't know if you guys ever use these Apple pencils. They're pretty amazing. I always avoided styluses. They're really nice, but I'm still figuring out how to exactly use it. Believe it or not, I think it actually improves my handwriting, if you can imagine. That's how bad my handwriting is. But I think my handwriting is kind of jerky in general, and it kind of like smooths it out a little bit. That's kind of funny. Not that it's good by any means, but anyway. Other questions? Okay. Okay. Yeah, sorry. Yeah, so we didn't use this piece at all, the zero component, because we picked an interval 0.1 on either side of it, right? So it didn't come into play. If we wanted to use that one, we would probably want this one on the right then, so we have an equal interval. Yeah. But since we have these two pieces that were really, really close, it just made sense to get as close as possible and then use those, right? Yeah. Yep, good thought there. Other thoughts? Someone said, why is there a 1/2 in front of the equation? Because what we're doing here, this is kind of the best way to think about it. We're taking the average rate of change from two places, right? One's too big, one's too small, and then we average those two things. And so when you have two numbers and you want to average them, you add them together and divide by 2. So that's what's going on here. You add them together, 1, 2, divide by 2, and then you average that. It's kind of confusing when it looks like this because this is a compound fraction, right? It's like a fraction inside a fraction thing. And so we can just take the 2, dividing by 2 is the same thing as multiplying by 1/2. And so it's just a way to simplify that down and make it not a compound fraction. That makes sense, Sebastian?
So then what's it called? Are we taking the number that we got from the top, like the 0.94 minus the 0.89 and all that? We're doing that. And then when we get that and we divide it by the 0.1 that we have right there, we get that number. And then we take that number divided by half.
So yeah, you do this, the thing I'm doing in green.
Yeah, we
You
get
get a number out of that, and then you either divide it by 2 or multiply by 1/2, which is the same thing. Multiplying by 1/2 is the same thing as dividing by 2.
Cool. Thank you.
Other questions? Yeah, thank you for clarifying that. Anything else? Keep them coming. Nothing else in the chat. So did we look at that one before? I think we did, right? So we looked at this Kingfisher example previously where we were looking at the average rate of change of this fish or this bird diving into the water. And we're going to revisit the same function, but think about the instantaneous rate of change, right? So on this thing that I'm showing right here, this one at the bottom of the page, we just said that the average rate of change was 10 feet per second downwards. It was negative. And now what we're looking at is we're going to hone in on a specific location on the graph and think about what the slope of the tangent line is, right? So it's a different look at the same function is what I'm trying to say. All right, so we're going to estimate the velocity at t equals 1. So let's just go back to the graph real quick. T equals 1 is right here. And so we're looking at this part of the graph, and we want to estimate this right here. In fact, is that graph on the other page? Why do I keep going back here? Did I put that down here? I should have. Maybe there's room. Okay. So we're going to estimate it and then calculate it exactly. I would actually like you to take a second and think about what the estimate would look like. So we're going to do this exact same thing again that we just did a second ago, just right down here, except instead of pulling the values out of a table, we have a function to plug numbers into. And if we want to look at t equals 1, we need to choose some points around 1 to look at. So maybe we could all just get on the same page and think about what that might be. Maybe I'll just write something down and let you think about it for a second. So what we want to do here in A, and try not to write too big here because we have a lot more to write down below there. We want to estimate the derivative at 1. That's what A is telling us to do. And we're going to approximate it in part A by doing that formula we just did. And so let's look at the average rate of change. Let's go from 0 to 1. And let's go from 1 to 2. So I'd like to just take a second and just let you at least try to write down the formula of what that would look like. If you don't have a calculator, this one actually isn't too hard to plug numbers into. At least if you can get the next step, like what does the function value look like? This equals 1/2 of what? Let's just spend a few minutes on that. It's good, helpful to think through this while I'm here, and we can clarify any misconceptions. Make that bigger too. Is that helpful? No. There we go. My normal classes, this is when I put on music. Josh was talking about that. I love throwing some music on in this, but just not there yet. Can't figure it out. I just hate the silence. I hate the awkwardness. All right, I'm gonna slowly write down the next step and let me know what you think. Does that look okay so far? These values I'm showing, h of 1 minus h of 0 over 1 minus 0, right? This is the average rate of change from 1 to 0, or 0 to 1, and then from 1 to 2. And we're just going to take these things, and we need to use this function to plug them into, right? So h of 1 is plugging a 1 in, right? H of 0 is plugging a 0 in. H of 2 is plugging a 2 in. And we just get numbers out, and it falls out kind of easily. Assume okay? All right, let's go ahead and finish this one off then. So I plugged the numbers in. This one's not that hard to plug numbers into. But I did it ahead of time. When you plug a 1 in, you get 14. When you plug a 0 in, you get 20. So that's minus. And then 2 minus 1 is 1. And then when you plug a 2 in, what did I get? I got 0. Minus 14. Super easy to calculate, right? Oh, let's add the units. Let's not forget about that. So the units here are feet on the top and seconds on the bottom. So our final units will be feet per second, right? So just helpful to kind of note that early on. And so we get a nice easy answer. This turns out to be 1/2 minus 6 minus 14 minus 10 again. And I'll just remind you, it's negative because the bird's going down. And it just happened to be the same as it was last time. It's total coincidence. Usually not the case. Actually, it's funny. It's an application of the mean value theorem, I think. Sometimes we get to that. I have to remember this for later. What's about the estimate? Just an estimate.
Can you repeat that, please?
Sure. So we were estimating the average velocity on this one. And so we were looking a little bit before the point we cared about and a little after the point we cared about. So we care about the point t equals 1. So that's why we looked at from 0 to 1 and then from 1 to 2, right? So if the point we care about is 1, we will look a little bit before it and a little bit after it. Right, we cared about this point. And so that's why we did 0 to 1, 1 to 2. Even better would have been like 0.5 to 1, 1 to 1.5, right? If you kind of squeeze in on 1, you get a better estimate. But then you have to plug fractions in. So we were trying to avoid that. So anyway, that's why I chose those two intervals. And so then the first one, this, right? This is just this average rate of change. And this one is just that average rate of change. And then we just plug the numbers into the formula to get these numbers. So like 14, for example, was h of 1. And 20 was h of 0, etc. Oops. Does that clarify a little for you? Is that the sort of thing you're hoping for? I'll assume that was a big resounding yes, unless you say otherwise. All right. What we really care about is the exact value, which is more important for sure. There'll be questions like this one. There'll be questions to estimate it. I'll put a question on the test that asks you to estimate it for sure. But what we really care about is this exact value, doing this thing in the box. Right? This is the thing that we've been building up to. It uses limits. We're going to use the things we practice, the techniques, and we get the exact value of the instantaneous rate of change. So this is really what we want to do. And so let's do the exact same thing here, except we'll calculate the value exactly using the exact limit definition. And we need a little bit more space for that because it's usually a little bit more involved. So part B would be doing the limit definition. So I'm just going to write the thing. I'm just going to copy this thing down, right down below in this context. So we care about the point 1, right? So we're going to do h prime of 1 is the limit as t is approaching 1, because that's, again, the point we care about is 1. And so then it becomes this. All right, so what I'm trying to say here is in the above definition, the b is 1. Right? That setup seem okay? All I've done is just plug a 1 into the above formula. All right, so let's just start plugging stuff in, right? So, and I mentioned this last time, but I'll just remind you again up here, right? I said all this stuff last time over here on the right. The f of x is just going to be the function. X is just a variable. In this case, it's a t. These two things, which are these two things, those are numbers. So f of b is b plugged into the function, right? And b is just the number. So the things on the right are going to be numbers. The things on the left are going to have variables. And so let's do it. All right, so h of t is just the thing right here, right? This is h of t. And so that's going to go right into the h of t spot. Right? And so that's going to be this then. And then h of 1, we just found out from the previous thing, when you plug a 1 in there, we got what, 14. Except I forgot to write the limit, so I'm going to have to slide this over in a second. Gonna move, oh no, I snagged that other thing. I forgot to write the limit in there, that's why I'm sliding this over.
When you move it over there, I can't really see it.
What's that?
Still can't really see it.
Are you using a computer?
Yeah,
Are you in full screen mode?
yeah.
How's that? I don't want to get too small here.
It's okay.
Okay. Let me also just try to label this. I should have done this previously too. If I slide this down. Right, this is the h of t. This is the h of 1. What do you think? This is usually the part where people get a little confused. Seem okay? Because if that makes sense, at this point, we're just doing the things that we know how to do, right? It's going to be indeterminate. We're going to factor and cancel. We know how to do this from now. So thoughts? Seems okay? All right, let's just do it then. So let's just keep going. And we just simplify things down, like I said, and we'll use the techniques that we learned, et cetera, et cetera. So this is the limit as t goes to 1. So just do 20 minus 14 to get the next step. 20 minus 14 is 6. And it's indeterminate. You can double check that, but if you plug a 1 in there, on the bottom, you clearly get 0, and then the top, you'll get minus 4, minus 2, plus 6, right? So that's going to be 0 over 0. I'm doing good on room here, doing okay on room. And so we should factor and cancel this one. And I hope that's not super surprising to people, right? There aren't tons of options. We're either combining, conjugate, et cetera, et cetera. The only one that applies here is factor and cancel. We need to start feeling kind of comfortable with that. So let's do that then. Let's factor this one. It's kind of tricky to factor, right? But I know that the whole point of factoring is to cancel out the denominator. So I know that one of the factors is going to be t minus 1. It's because we're in a math class and I know that that's going to happen. This isn't a real world application where maybe this wouldn't work. It's going to work. And so that just gives you a hint about how to proceed, right? And that would help you realize that it factors into this other piece. It's kind of hard to get the 4t minus 6. It's not impossible. It would take a little bit of thought. But if you know one of the factors is t minus 1, that should happen pretty easily, right? And that was nice because the t minus 1s just cancel. That was the whole point. I can't stress that enough. That's how we knew that that would be the factor. And so now we can plug a 1 in. You can plug a 1 into minus 4t minus 6, no problem. That's minus 4 times 1 minus 6, again, is minus 10 feet per second. I'll just add the note at the bottom. It's kind of an important note. The three times we've looked at this function, we got minus 10 every time. Total coincidence. And I always go back and forth about whether I should just come up with another example so that they're different, but I like this example. So I'm just going to make this note. So our estimates, let me write that over. So our estimates for the average rate of change, instantaneous rate of change, and the exact rate of change were all minus 10. This is a coincidence. I just don't want you to think like you should always get that. It's a coincidence. I don't know. Just don't expect it all to happen. Sorry, wow. Page a little bit. There you go. There's no, should be an N in there. Coincidence. Did I spell coincidence? No clue. How are we doing here? I'm pretty good. On the next page, yeah. Okay. What? Oh, because they're all the same. Yeah, yeah. I mean, most of the time, I probably wouldn't give you one function and ask you to do the same thing, do it 3 times. So I would probably split it up, and so you don't have that feeling. All right, thoughts at all about that? Oh, great on time. I think I would like to just look at the next page and then look at our quiz here. No questions? Is that the only example I do there? Yeah, so I would say this is the only exact example I do, but there's some on the homework for next week. So usually let, just like we've done in the past, let people look at the homework, maybe come up with a question that you want to look at, and we can look at some together Monday, Wednesday. Oh, we don't have class Monday, so Wednesday. Right, no class Monday because of the President's Day. President's Day, right? Some holiday. Okay, let's just tie this up, button it up, and talk about what this looks like. We already kind of know what this looks like, right? So this page is all about visualizing rate of change, like you can see. We've already been kind of visualizing it with some of these graphs or some of these hypothetical images up here, right? But sometimes it's nice to put it all together in some summarizing picture. And so the 3 things at the top here, what we're kind of focusing on here, which is that if you have a positive rate of change, that means the graph is increasing. If you have a negative rate of change, that means the graph is decreasing, right? Because if it's the slope of the tangent line, it's going up, it's going to be positive, it's going down, it's negative. And moreover, a really, really big thing later in the course and just in calculus in general is thinking about where there's no rate of change. Where is the graph flat, right? So I like to talk about this in the context of a trip to Philadelphia. So let's say that the graph down here represents Philadelphia. I'm sorry, our trip to Philadelphia, we've got like Fitchburg down here at the bottom. And then we drive along the way, and then the end point here is like Philadelphia. So maybe Philadelphia is here. And so it's like the distance from Fitchburg is the y-axis. So if that's a distance from Fitchburg, it's like we started going towards Philadelphia. We got like most of the way there, and then we turned around because we forgot something at home or something. I don't know. We left something at the gas station that was in, where is that? That's like Worcester or something. And then we had to go all the way back, right? So we got closer, we turned around, and then we went back. And so there's some questions at the bottom here, just kind of help us think about this situation. So let me go ahead and label a few points, and then let's talk about those points. So let's label this point right here. A. And let's say this is the point 2. Let's make B right below that peak. Okay. C is going to be right in the middle there. D is going to be right here. And then let's just leave it like that. Okay. So thoughts about where the rate of change is the largest, right? That's the first question. Where is the rate of change in this picture the largest? Or what does that mean? How do we know what's the largest?
Where it's the highest?
Yeah, so 2 answers. I heard, I think it was Janetta say where it's the highest. And what did you say, John? And then John saying is where it's the steepest, right? So if we're thinking about the rate of change, maybe we should just write this. Rate of change equals the steepness of the graph. Right? It's the slope of the tangent line. And so if we want to know where it's the biggest, we'd be looking for the place where the graph is the steepest. So where is that?
Where I'd say B.
So this is pretty steep here from A to B, but I would argue that this one over here is actually steeper on the right. Right? If we look at this point right here, like this section of the graph, let's label this, let's star it right here. I think the star is the biggest part because the graph is the steepest. And so someone has said a couple times, I think someone remotely was kind of repeating that maybe they think that B, this location, is the biggest rate of change. That is one of the highest points on the graph, but it's actually flat there, right? In other words, the slope of the tangent line, if we drew the tangent line, it would look like this. That has a slope of 0. And so B, in terms of rate of change, actually has no rate of change. And so that's actually one of the answers to the next part. Right, this part right here, where is there 0 rate of change? The next question. That's going to be at the peaks. So B is one of those. Let's maybe we'll star those with another color. Let me put a green star there, and a green star there. The green stars are where there's 0 rate of change. Right? The graph is flat there. In other words, the slope of the tangent line is 0. That's a really important point. Again, that's something where we hone in on once we look at derivatives a little bit more. We hone in on how do we find these maximum points? Because that's an interesting point. Those B and D is where we turned around, right? B is where we were driving towards Philadelphia. We forgot something. We turned around and started going back. We cared about our trip or whatever. We were trying to analyze the trip. That would be an important point, right? D is where we were heading back towards Fitchburg, and then we turned around and started driving back towards Philadelphia. So again, something changed there. There was some kind of event. So those are interesting points usually in functions. Questions about that 0, like what rate of change means? I feel like people are a little bit confusing it with biggest points on the graph. I'm talking about steepest or not steep. Thoughts? Seems okay? So I've already mentioned this. The next question is what's happening at number 3. Let's go ahead and label number 3. Let's say 3 was this section of the graph. What's happening there? I've already said it a couple times, but just going back towards Fitchburg, right? And so the tangent lines are negative there. So direction matters again, just kind of emphasizing that. So 3 is going back towards Fitchburg. But the thing I really want to emphasize, that means negative rate of change because direction matters. All right, I forgot to add 0.4. So I'm going to add another dot on the line here. I'm going to put it right here. Everyone see this number 4 I'm kind of circling right now. I just added that dot there. Because the next question says, how do we draw a line whose slope is given by the average rate of change from 4 to 2? We've done that a bunch of times. Let's throw a line in there. Right, so the purple line here tells us the average rate of change. All right, the last two questions are also relevant for future, what we're doing in the future here. So the last two questions are, where is the graph slowing down? And where is the graph speeding up? I'm sorry, where is the car slowing down and where is the car speeding up? How can we tell if it's slowing down or speeding up? What do you think about that, John? Yeah, so again, when we're thinking about velocity or rates of change, we're thinking about the tangent line. So slowing down would mean the tangent lines are flattening, and speeding up means the tangent lines are becoming more steep, right? So slowing down would be somewhere between A and B, for example. And also from, say, C to D. Let me do this. So from A to B and C to D. And the way you think about that is because the tangent lines become flatter. Or if we thought of the tangent line, let me kind of draw a couple tangent lines on here between A and B. Early on, it's kind of got this slope. As we get closer in B, it's flattening out, right? So it's decreasing. Similarly, if we went from C to D, C is like kind of going kind of fast towards D. But as we get closer to D, the tangent line flattens. Right, so the places where the tangent line's flattening is slowing down. And then speeding up the opposite. So it'd be like B to C or beyond D, for example. So speeding up could be from B to C and beyond D. Because the tangent lines steepen. Let me try to make that a little more legible. Steepen, is that even a word? Let's just say become more steep. Right, the slopes are going up in a positive or negative way. Right, B to C, we're going faster, but we're going faster negatively, and beyond D, we're going faster, but we're going faster positively. I don't know if that.